So in this next part that follows from our equation of hydrostatic equilibrium, we're going to talk about the Eddington luminosity. And again, this follows from hydrostatic equilibrium. This was actually first come up with by Arthur Eddington, who's the same guy that came up with the Eddington approximation that we used earlier in the term to derive our second form of the moments of the radiative transfer equation in terms of mu. So the basic picture of the Eddington luminosity is it is the luminosity at which hydrostatic equilibrium is attained, and there is a balance between radiation pressure acting outwards, and this in particular is for a star. So the Eddington luminosity is something you define for a star, and the force of gravity. Um, so the force of gravity. So I guess technically the balance is against the force of gravity versus the force of radiation pressure. And when this happens, when these two forces are equal, then you're at the Eddington luminosity. In deriving this, we're going to make a few assumptions. We're going to assume spherical symmetry. We're going to assume hydrostatic equilibrium. So that's what we did in the past lecture. And then finally, the approximation that Eddington made when he came up with this was that the opacities were all set by electron scattering, by Thomson scattering. And we'll discuss what that approximation means later on. To start with, we will, similar to when we started deriving the equation of hydrostatic equilibrium, we're going to write an expression for a mass element dm at the surface of the star. So this mass element dm is experiencing downward force due to gravity, and then upwards force due to radiation pressure. So the gravitational force is going to be gmm times dm, our mass element differential mass, over r squared, and m is going to be the interior mass, so the mass of the star in the case of a star. So the mass element is going to experience gravity pulling it down. At the same time, in stars, we have radiation generated in the stellar interior, and the radiation is going to exert a pressure on this differential mass element as well. The pressure due to radiation is something we've actually thought about before. So we can write an expression for the pressure due to radiation using what we learned from those radiative moments that we derived. So you might remember that our third radiative moment, that K integral, was related to the radiation pressure. And what it told us is it said that the pressure of radiation is equal to technically the radiative flux over C, but we'll say flux over C. So this, for pressure due to radiation, we can then write flux as luminosity over 4 pi r squared. Remember, r is the stellar radius, and then all of that over C, and that'll be radiation pressure. If we want to get the expression for the force of radiation pressure, we're going to have to think about opacity. So the opacity in the stellar atmosphere is going to determine exactly how that radiation pressure converts into a force, because the pressure of radiation is going to be equal to the force over area. And then you'll remember that the definition of opacity was the area over mass. So this was our second definition of opacity, the mass opacity. And in this scenario, we're thinking only about scattering. So this means that the force due to radiation is on our mass element is going to be the pressure, the radiation pressure, times our opacity kappa times m, our mass of a scattering object. So then we can write the force due to radiation pressure here by substituting in the added two terms for the opacity. So it's going to be luminosity times the opacity times the mass of a scattering a species over 4 pi r squared times the speed of light. So next stage is we're going to set these equal to each other because the Eddington luminosity is the luminosity where the force of gravity is exactly balanced by the force due to radiation. So that's going to be gm dm over r squared equals L kappa m over 4 pi r squared c. And we're going to assume here that this is our unit mass dm because it's going to be the same mass element that is experiencing gravity is also going to be providing the scattering. So if we solve for the luminosity, then we're going to get 4 pi g m, and that m is the mass of the star, c over kappa, when kappa is the opacity. And kappa, this is defined as the Eddington luminosity. So this is when radiation is balanced by gravity. So you're not going to have any loss of mass due to radiation. Oh, actually, the one thing I should point out is that kappa, if you're dominated by Thomson scattering, then your kappa is going to equal the cross-sectional area of an electron, the Thomson scattering, over the mass of a proton. The reason for that being that that's the mass element. The protons are going to be most of the mass because they're about 1,800 times more massive than electrons. So they're going to be the objects of the stellar atmosphere that could potentially be lost in a flow if radiation pressure was too strong. So kappa is going to be sigma T over MP. So that lets us rewrite our expression for the Eddington luminosity in terms of, now we have it in terms of the Thomson cross-section. And this is the classic Eddington luminosity. So this is the form of the equation that Eddington himself derived, and he assumed that all the opacity came from electrons, from Thomson scattering, which is why he didn't include the opacity kappa, just the Thomson cross-section, which it turns out that this is actually not always true, because in stellar atmospheres you can have opacity, as we know, because we've been talking about that this term, you can have opacity provided from other species other than electrons. Okay, so this is the Eddington luminosity. The next important piece of this is if a star is below the Eddington luminosity, then the photons are going to be, the pressure due to photons is going to be weak enough comparatively that it's not going to drive an outflow of mass. If you have a case where a star is accreting, so you have mass falling onto a star from an accretion disk, which then breaks our spherical symmetry that we said earlier. But for now, in that case, the potential energy that you have from material falling onto the star can be balanced by energy radiated away via luminosity. So you can say that the luminosity due to accretion is going to equal m dot c squared. So that's the energy of the accretion times some factor epsilon. So m dot's the accretion rate, c is the speed of light here. And then our epsilon is going to be our fraction of energy that's radiated away as luminosity. Now, importantly, if this accretion luminosity is greater than the Eddington luminosity, which remember the Eddington luminosity is the point where radiation pressure balances gravity. If you exceed that luminosity, then your radiation pressure is stronger than the force of gravity. And instead of being able to accrete onto the star, you won't be able to have accretion because the radiation pressure is going to be too great to allow material to fall onto the star. So if your luminosity of this flow is greater than the Eddington luminosity, you're not going to have accretion. You can find a limit on what mass accretion rate is allowable then using this expression for the luminosity due to accretion and this Eddington luminosity that we defined above. So we'll say that the limit on the mass accretion rate is going to be when these two luminosities are equal. So our expression from before, assuming the form that only pays attention to Thomson scattering, equals our accretion luminosity. And if you solve this for the accretion rate, and we'll call that the Eddington accretion limit, then you get the following: 4 pi gm times mass of a proton over this epsilon fraction speed of light and the Thomson cross-section. So again, this is assuming that the major opacity source is electrons here. So these are all things you know, except for one. So you're not going to know necessarily this epsilon factor. So if you really want to find the Eddington accretion rate for something, you need to know what this factor is. The lower limit, so it's a fraction ranging between 0 and 1. The lower limit's going to be 0. And a physical scenario where that might be the case is if you dropped material radially into a black hole. It would take all of its potential energy away with it, and none of it would be emitted as luminosity. More typically, values of around like 0.1, or I'd say 0.01 to 0.1 are more typical for accretion disks, because usually accretion flows also are not truly going to be spherically symmetric. If you take high energy, then you'll learn a little bit about black hole accretion. And again, the accretion rates around black holes probably are closer to like 0.1 on an accretion disk anyway. But this is actually an open question for many physical scenarios, is exactly how that efficiency factor eta depends on the parameters of what you're looking at. But something like 10% is probably a decent assumption most of the time. Okay, so Eddington luminosity is theoretically the limit in terms of what luminosity is possible, and the Eddington accretion rate is theoretically the maximum accretion rate that you can have onto an object, because above that accretion rate, your luminosity is going to push away accreting material. However, you've probably heard the phrase super Eddington before, because there are some scenarios where accretion can become super Eddington. So one of these is that we made the assumption of spherical symmetry, but accretion is not usually spherically symmetric, especially when it's around for a star or a black hole being fed by an accretion disk. So for cases where you don't have spherical symmetry and maybe you don't have a steady state, then you can get apparently super Eddington luminosities. There are other possibilities that can allow you to physically attain luminosities above the Eddington approximation that basically all boil down to limitations in the approximations that we've made. Besides that, I think this is something that, again, you'll probably see again in future astro classes. The important thing to take away from this is that the Eddington luminosity and the Eddington accretion rate both come from the assumption of hydrostatic equilibrium, because hydrostatic equilibrium is just setting some pressure equal to some gravity, which gives you an equilibrium state. And when specifically the pressure is due to radiation, then that will yield the Eddington luminosity.